a shimmer of untold power resides within a humble, silvery white metal. It is not gold, nor platinum, nor any of the celebrated elements that have driven economies and empires. This is thorium, an element named after Thor, the Norse god of thunder. For decades, it has been the great silent promise of the energy world. A source of power so vast and clean, it has been likened to a myth. Like the solid-state batteries we have long been promised, thorium has remained just over the horizon, a tantalizing mirage of a perfect energy source that never quite materialized. Whispers of its potential have echoed through the halls of science since the dawn of the atomic age. Yet it has remained dormant, a sleeping giant. But what if the giant is beginning to stir? What if the myth is on the verge of becoming reality? The story of thorium is not just about a futuristic technology. It's a tale of a forgotten past, a present-day race between nations and innovators, and a future that could be radically rewritten. The pieces are falling into place, not in a sprawling government laboratory, but in workshops and startups, driven by a new generation of pioneers. The question is no longer if thorium can change the world, but who will be the first to unleash its thunder. To understand why this seemingly miraculous element was left behind, we must journey back to the very cradle of nuclear energy, Oak Ridge, Tennessee, in the 1960s. Here, amidst the Cold War's atomic fervor, a visionary physicist named Alvin Weinberg championed a radical new type of reactor. It wasn't designed for the uranium that had become the world standard. Instead, it was built to run on thorium, dissolved in a molten salt. For 5 years, from 1965 to 1969, the molten salt reactor experiment was a resounding success. It operated flawlessly, proving that a thorium reactor was not just a theoretical possibility, but a practical reality. Weinberg believed this technology was the key to a future of safe, abundant, and clean energy. But his vision was not aligned with the era's priorities. The dominant nuclear powers were focused on uranium and plutonium, not just for energy, but for weapons. Thorium reactors were inherently difficult to weaponize. They didn't produce the plutonium needed for bombs. And so, despite its proven safety and efficiency, Weinberg's project was defunded. The molten salt reactor was shut down, its secrets buried, and the world proceeded down the path of uranium, a path that would be defined by both immense power and persistent problems of waste and safety. For half a century, Weinberg's dream lay dormant, a footnote in the history of nuclear science. But an idea that powerful never truly dies. Decades after the silence fell at Oak Ridge, that abandoned vision is being resurrected, not by a government superpower, but by a nimble and ambitious startup in Denmark. Copenhagen Atomics, a name that evokes the pioneering spirit of early atomic science, is reimagining Weinberg's reactor for the 21st century. Their approach is both a tribute to the past and a leap into the future. Instead of constructing monolithic billion-dollar nuclear plants, they are designing small, modular reactors. The concept is revolutionary in its simplicity. Build the reactors in a factory, like cars on an assembly line, and ship them to wherever power is needed. Each reactor, compact enough to fit inside a standard shipping container, is designed for mass production, scalability, and radical cost efficiency. They call it the Copenhagen Atomics waste burner, a name that hints at another of its remarkable capabilities. This isn't just about creating a new energy source. It's about solving the problems of the old one. The goal is to create a decentralized network of power generation, bringing clean energy to remote communities, industrial parks, and developing nations without the colossal upfront investment and decade-long construction timelines of traditional nuclear power. It's a vision of democratized energy, built one small, powerful box at a time. At the heart of this Danish innovation lies a unique and elegant process of nuclear alchemy. To understand how these small reactors can promise so much, we must delve into the atomic dance of the thorium fuel cycle. Unlike uranium-235, the most common nuclear fuel, thorium itself is not fissile. It cannot directly split to release energy. Instead, it is fertile. When a thorium atom, specifically thorium-232, is placed inside a reactor, it can absorb a stray neutron. This simple act of absorption triggers a transformation. The thorium atom becomes thorium-233, which is unstable and quickly decays into protactinium-233. This in turn decays over the next month into a new element, uranium-233. And uranium-233 is special. It is a highly efficient fissile fuel capable of sustaining a powerful chain reaction. This is the magic of thorium. It breathes its own fuel. In a properly designed reactor, the process can become self-sustaining. The uranium-233 fissions, releasing energy and more neutrons. Some of these neutrons go on to split other uranium-233 atoms, continuing the chain reaction, while others are absorbed by new thorium atoms, breeding more fuel. Incredibly, a thorium breeder reactor can create more fuel than it consumes, all while operating. This elegant cycle is the key to its power, but it requires a very specific and unconventional environment to work. The secret to unlocking thorium's potential lies not in the solid fuel rods of a conventional reactor, but in a liquid core of molten salt. The molten salt reactor, or MSR, is the technology that Alvin Weinberg pioneered and that Copenhagen Atomics is now perfecting. Imagine a nuclear reactor where the fuel isn't a solid ceramic pellet encased in metal, but is instead dissolved into a scorching hot, clear liquid salt mixture. This liquid, a fluoride salt cocktail known as FLNIAK, flows through the reactor core in a continuous loop. Inside the core, it achieves criticality, heating up to around 700 degrees Celsius. This superheated salt then flows out to a heat exchanger, where its immense thermal energy can be used to generate steam for turbines, create industrial heat, or desalinate water. The process is fundamentally safer than traditional water-cooled reactors. The MSR operates at atmospheric pressure, eliminating the risk of the high-pressure explosions that were a factor in disasters like Chernobyl and Fukushima. Furthermore, the safety is passive. If the reactor ever overheats, a frozen salt plug at the bottom of the vessel melts automatically, and the liquid fuel drains by gravity into a passively cooled containment tank, where the nuclear reaction immediately ceases. This inherent safety, combined with the ability to continuously reprocess the liquid fuel to remove byproducts and add new thorium, makes the MSR the perfect vessel for the thorium fuel cycle. While the concept of a molten salt reactor is elegant, the engineering reality is incredibly demanding. The core of the reactor is a crucible of extreme conditions. The FLNIAK salt, while an excellent carrier for the fuel, is ferociously corrosive at 700 degrees Celsius. It will eat through standard steel as if it were sugar. Finding materials that can withstand this constant chemical assault for years on end is one of the greatest challenges in modern materials science. Copenhagen Atomics is tackling this head-on by developing custom stainless steel alloys and other advanced materials capable of enduring the harsh environment. Furthermore, everything inside the reactor must operate flawlessly in this intense heat and radiation. Pumps, valves, and sensors cannot be ordinary. Copenhagen Atomics has engineered specialized components, such as magnetically levitated pumps that have no bearings to wear out, ensuring they can circulate the molten salt reliably. Their modular design also presents a clever solution to material degradation. Instead of building a reactor meant to last 60 years, their entire containerized reactor module is designed to be fully replaced every 5 years. The old module is taken back to the factory, its valuable components are recycled, and a new, pristine module is slotted in its place, ensuring the system remains at peak performance and safety. The culmination of all this research and engineering is fast approaching a critical milestone. While computer simulations and material tests are essential, The ultimate proof of a reactor's design is to actually turn it on. Copenhagen Atomics is preparing for this moment. They have partnered with the prestigious Paul Scherrer Institute in Switzerland, one of Europe's leading research centers, to conduct the first critical test of their reactor design. This will not be a full power demonstration just yet. The initial plan is for a 30-day low-power run using uranium fuel dissolved in the molten salt. The primary goal is to validate the reactor's core physics, its control systems, and the performance of its unique components in a live nuclear environment. This critical test will be the moment the digital models meet physical reality. Following the initial run with uranium, the team plans to gradually introduce thorium into the salt mixture, taking the first crucial steps toward proving the breeding cycle. It is a high-stakes, methodical process where every piece of data will be scrutinized by regulators and the global scientific community. The world will be watching to see if the Danish startup can succeed where a Cold War superpower gave up. While Denmark and Switzerland prepare for this pivotal test, another global power has been moving silently and swiftly in the background. In August 2023, China announced a significant milestone from its own molten salt reactor program. At their facility in the Gobi Desert, Chinese scientists successfully operated a thorium-fueled MSR, and critically, they managed to breed new fuel. They were able to demonstrate the conversion of thorium into protactinium-233, the direct precursor to the coveted uranium-233 fuel. Their system also proved the viability of continuous online refueling and reprocessing, removing the fission products from the liquid fuel while the reactor was still running. This was a major step forward, solving one of the key technical hurdles of the MSR design. However, China has not yet announced that they have achieved a full breeding cycle, where the reactor produces more fuel than it consumes. The race is now on. While the West is focused on smaller, modular designs driven by the private sector, China is pursuing a state-sponsored, large-scale approach. The question of who will be the first to build a commercially viable, self-sustaining thorium breeder reactor is now one of the most pressing in the energy world. The technological race is paralleled by an equally radical innovation in the business of energy. Copenhagen Atomics does not plan to simply sell its reactors. Their business model is to become a global energy provider. They intend to build, own, and operate their containerized reactors, and then sell the heat they produce to customers. This heat-as-a-service model completely upends the traditional nuclear industry. It would allow developing nations, which have never had the billions of dollars or the specialized infrastructure to build a conventional nuclear plant, to access clean, reliable baseload power. A factory, a remote town, or a desalination plant could simply sign a contract for a steady supply of heat or electricity, and Copenhagen Atomics would deliver and manage the power source. This eliminates the massive financial and technological barriers to entry that have kept nuclear power confined to a small club of wealthy nations. It's a disruptive vision that treats energy not as a massive infrastructure project, but as a scalable, deployable service. This model could fundamentally change the global energy map, bringing power and prosperity to regions that have long been left in the dark. Beyond generating power, the thorium fuel cycle offers a profound solution to one of the most persistent problems of the atomic age: nuclear waste. Conventional uranium reactors produce waste that contains highly radioactive elements like plutonium and americium, which remain dangerously radioactive for hundreds of thousands of years. This long-term waste requires deep geological storage, a complex and politically contentious issue that remains largely unsolved. Thorium reactors, by contrast, produce far less waste, and the waste they do produce has a much shorter half-life. The majority of the byproducts become safe in just a few hundred years, a timescale that is far more manageable for secure storage. Even more remarkably, thorium MSRs can be designed as waste burners. They can actually be started up using the plutonium and other long-lived elements from the waste of existing uranium reactors. In essence, they can consume the most problematic legacy waste from the first nuclear age.
turning a multi-generational liability into a valuable fuel source for the next generation of clean energy. This potential to clean up the past while powering the future is one of thorium's most compelling advantages.
The path forward for thorium is not without obstacles. The technology, while promising, is still in its nascent stages of commercialization. The ultimate milestone, achieving a net positive breeding ratio in a commercially operating reactor, has yet to be reached by any team in the world. And perhaps the largest hurdle is not technical, but regulatory. The world's nuclear regulatory bodies are structured around solid fuel, water-cooled uranium reactors. Approving a radically new design based on liquid fuel and a different fuel cycle will require a paradigm shift in how regulators think about safety and licensing. This bureaucratic process could be the biggest bottleneck, slowing down the deployment of thorium energy. Yet, despite these challenges, a palpable sense of momentum is building. The race is on between different nations and different approaches. The potential impact is staggering. A world with a decentralized, safe, and truly sustainable energy source, capable of lifting billions out of poverty, cleaning our air, and mitigating the threat of climate change. The thunderous promise of thorium, first glimpsed by Alvin Weinberg more than half a century ago, is finally rumbling. Thorium may not just power the future, it might rewrite what the future looks like.